We now come to a very important theorem in topology, which is that of an intermediate value theorem. And you might have already seen it in your calculus course before. And it is a consequence of the connectedness of a space. And it says that if you have a let us say a function f from, say, a closed interval to the real line, so the graph of this function will look like this. Now let us take 2 points, x0 and y0 in R, and so on the graph you will see a point which is x0 fx0, and here this is y0 fy0, and now we have this interval on the vertical direction. This is f of x0 and this is f of y0. So if you choose any point, let us say here, let's say alpha, so this is the line y equals alpha. So given any alpha belonging to the interval fx0 fy0, there exists a z0 belonging to the interval x0 y0 such that f of z0 is equal to alpha, which means that the line y equal to alpha must intersect the graph of the function f. So this is the point z0 that we want here, and this point is precisely z0 comma alpha. So this is the intermediate value theorem for continuous functions on the real line, and this you might have seen in calculus. But the theorem in its full generality is given as follows. Let X be a connected space and Y be a simply ordered set with the order topology. And now consider a continuous function f from x to y, and because y is simply ordered, so for any 2 points a, b in x and any r in the interval fa to fb, there exists a point c in x such that f of c is equal to r. Notice that here x is no longer a simply ordered set, so here the condition that we wrote for the interval subinterval of the real line does not make sense because there is no simple order on x, but the simple order is on y. So you can still talk about the interval fa to fb, and you can choose a point, any point, alpha that we chose here. This is denoted as r, and the statement says that there exists a point c in x such that f of c is equal to r. So let us see a proof of this theorem. So for the proof, let us take 2 sets. The first one is just fx intersection with the ray from -infinity to r. So remember that this was just the set of points in y such that x is less than r, and b, I take the intersection of fx with the ray on the other side, and this was the set of points in y for which r is less than x. Okay, so notice that a and b are non-empty, disjoint, and open subsets of fx in the subspace topology. So of course they are non-empty. It is easy to check. They are disjoint because we are taking the intersection with r to infinity and minus infinity to r, and these are disjoint sets. So a and b are disjoint, and they are open because these are open in the order topology. Open in the order topology. So they are non-empty, disjoint, and open subsets of f of x in the subspace topology. And if f of x is not equal to r for all x in x, then we have that the set fx is the union of a and b. This is because we have excluded r here, and so if fx is not equal to r, then fx is the union of these two sets a and b, and this is enough to reach a contradiction. So this is a contradiction, since then AB is a separation of f of x, which is connected since f is continuous, as f is continuous. Now, as an application of the intermediate value theorem, we can state the following result, that if f is a continuous function from 0, 1 to 0, 1, is a continuous function then there exists a point x in 0, 1 such that f of x equals x. So let us see a quick proof of this application that we have for the intermediate value theorem. So define a function g from 0, 1 to now minus 1, 1, and this function g is defined as g of x is equal to f of x minus x. Now note that since f0 is not equal to, if so suppose that there exists no point. Okay, so first suppose that fx is not equal to x for all x in 0, 1, then f0 is not equal to 0 and f1 is not equal to 1, but this implies that g0, which is f0 minus 0, so this is just f0, so f0 minus 0, this is just f0, and this must be greater than 0 because f is a function from 0, 1 to 0, 1. Similarly, g1, which is f1 minus 1, is less than 0 since f1 is less than 1. So G0 is greater than 0 and G1 is less than 0. And now we have, by the intermediate value theorem, there exists a point x in 0, 1 such that gx is equal to 0, because you had the graph of gx is something like this. At 0 it is greater than 0 somewhere here, and at 1, so this is 0, this is 1, so this is g0 and this is some g1, and so the graph of the function is like this, and so it must cut the x-axis at some point, and this is where gx must be 0, and this is what the intermediate value theorem says. So, but gx equal to 0, this is the same as saying that fx minus x equal to 0, or in other words fx equal to x. So we have found a point x for which fx is equal to x, and this is known as the Brouwer's fixed point theorem, and this is a very basic version of Brouwer's fixed point theorem. Brouwer's fixed point theorem, and this is a basic version, and there are much more sophisticated versions of the theorem which require different techniques to prove, but as a simple application of the intermediate value theorem we can show this result. So this brings us to the end of this week's lecture, and in the next week we will continue with the concepts of connectedness, and we will learn about path connectedness and local connectedness and local path connectedness, and we will see some examples of interesting spaces which have one property but not the other.